It might not be the right time. I might not be the right one.
Okay, for this problem, we're asked to find the volume of the solid obtained by rotating the region enclosed by x equals y squared and x equals square root of y about the y-axis. So here we see we're going to be integrating or rotating about the y-axis, right? So that means we're going to have to get everything in terms of y, all right? So for these graphs, though, just for the purpose of graphing, let's get the y's by themselves because we're more familiar with that. All right, so for this first equation, when we rewrite it, we're going to get y by itself, so we square root both sides, and when we do that, we get y is equal to positive and negative x square root of x. Okay, so here's our first function rewritten in a graphable form, and then this one, when we rewrite this one, we get we're going to square both sides, right? So we get y is equal to x squared, all right, which we know how to graph. So let's graph these two and see what goes on here. So let's say so here's our x and y there. So what we're going to have is basically here's 1, let's say, and here's a 1. Okay, so this first graph, this is going to look like the square root of x. So this will pass through 1, 1 and keep going that way. That's the positive one. And the negative one is going to be like this. So it's going to basically just go down, but be like a sideways U. Okay, so this is our positive. This is y equals positive square root of x. Or we can call this actually, I'll name it in terms of y. So that means that this is our x equals y squared. Okay, that's our sideways u. And then this one down here, when we graph that, that's x squared. So that'll go through and up like this. Okay, so something like that. So this is what looks like our upwards, our normal parabola. So this is our x equals, well, I'll write it on the left side so we know what's going on here. So this is going to be our x equals square root of y. Okay, so this is x equals square root of y. That's this one, the upward facing u. Okay, so the region enclosed is the stuff in between, right? So it's going to be this in here. All right, and let me blow that up on the next slide so we can see what it actually looks like. So here's our graph again, okay? And we're going to have x and y. Here's 1, positive 1. Here's a negative 1. And here's a positive 1. So we have something that looks like, it's basically this thing. Okay, so it's going to be a graph like this. Okay, so this is our x is equal to y squared. And then our other one looks like the following. So we have it going up like that. So this is our x is equal to square root of y. All right, so if we want to rotate this region here in between around the y-axis, what that means is we're going to have to take our axis of rotation, which is the y-axis, which is equal to x equals 0, right? That's the equation there. And we're going to take that and draw our radii. So here's the first one. So I'll shade this in so we know where we're going. So there's, we hit the region the first time. And then, so this is going to be our small r. And then we're going to go from our axis of rotation to the far edge of our region here, the far border. Okay, so that's our capital R. Capital R is there. All right, so what is capital R? Capital R is right minus left, so that would be square root of y minus left, which is 0. So that's just going to be given by the square root of y, okay? And then for the small radius, we have that is equal to right minus left, so this will be this function first, so y squared minus left, which is the x equals 0 line, the y-axis, so that'll be a 0, right? So we have capital R and little r, and then we need to know where do they intersect. So on the graph, we can kind of see that they intersected 0 and 1, but we could always solve for that, right? By setting the equations equal. So we have square root of y is equal to a y squared, and that only happens when we have that either y is equal to 0 or y is equal to 1. Okay, so this is our interval of integration. Our limits of integration are 0 to 1. We're integrating on dy along the y-axis there, and this is our capital R, and this is our little r. Okay, so let's set up our volume integral. So we have v is equal to pi times the integral from 0 to 1 of capital R squared, so that's going to be square root of y squared minus little r squared, which is y squared squared. Then we have our dy there, okay? So this is going to turn out to be v is equal to pi times the integral from 0 to 1 of y minus a y to the 4th, and then our dy, right? So let's continue this on the next slide. So we have volume is equal to pi times 0 to 1 of y minus y to the 4th, and then we have our dy. So if we integrate, we get y is equal to pi times y squared, and then a 1/2 in front, minus 1 over 5, and then y to the 5th, okay? And then we're integrating from 0 to 1, or we're evaluating from 0 to 1 now. So then this is going to be equal to, v is equal to pi times, and when we plug it in, we get 1 over 2 times 1 squared minus 1 over 5 times 1 to the 5th, and then this whole term back there, that's just going to be zeros, right? So then zeros go away. So we get a v is equal to pi times 1/2 minus 1/5, which is equal to pi times 5 over 10 minus a 2 over 10. So this whole volume is going to be equal to a 3 pi over 10, a positive 3 pi over 10.
But there's something about us I want to say, 'cause there's something between us anyway.